Yes, welcome to the last episode of our course Further Mathematics for SS3. And in this particular episode, we are going to be dealing with the topic known as conic sections. Now, conic sections, they are a very important part of mathematics because it's an intersection between mathematics and what I call technical drawing, which was one of my favorite subjects back in school. And conic section is quite interesting for a number of reasons. It goes way beyond what we normally treat in mathematics, and it helps us understand the fundamentals of mathematical formulas. So let's talk about one concept in conic sections, which is the parabola. And the parabola, we'll be talking on the parabola here. Now, the parabola, which is probably being displayed on the screen right now. So the parabola is basically a particular shape, and this parabola has a particular property which we explore in this course. So the parabola is a locus of a point moving in a plane such that its distance from a fixed point is equal to its distance from a fixed line. So that is the directrix, not passing through the focus. So in this case, what we're trying to say is that in this parabola, the distance from a fixed point, the distance of the parabola from a fixed point is equal to its distance from a fixed straight line. So which is the directrix, and that directrix will not pass through the parabola. So in short, what we're trying to say is that we have a diagram. We will have something like this, diagram like this. So we'll possibly have the origin. I'm having issues with my marker. So we'll probably have the axis like this. So now in this case, we have a parabola. This is basically how a parabola looks. Now imagine we have the directrix somewhere on the other side of the So assuming this is the directrix now. We also have the this is the y-axis, this is the x-axis. Now the axis is on the other side. I could represent it as a dotted line anyway. Now there's a particular point in this parabola known as the focus, right? Now when we look at it carefully, in this what we're trying to say is that in this parabola, the distance of this parabola, the distance of any point on, for example, let's have a point P. The distance of a point P, x, y, from the focus of the parabola is the same as the distance of this point P from that directrix. So that means if the length of from P to D is let's say x. Okay, let's not use x. If it is z, then the distance from P to F is also z. So now with this we can form a mathematical equation which gives us the formula for getting the equation of a parabola. I will leave that to you. You can check that out in your books and also verify your equations. Now the major thing concept here is not about the equations and the formulas. It's just about understanding the basics, because this is not mainly about calculations, about understanding how this thing works. So what I'm trying to say is that this focus from here to here is equal to the distance from here to here. That is basically what you need to know in a parabola. Now let's talk about the ellipse. Now the ellipse is basically a particular kind of shape. It's a special kind of shape, and when we are talking about the ellipse, which is probably displayed on the screen right now, so we have the ellipse, and this ellipse basically has a definition. It is the locus of a point moving in a plane, so such that its distance from a fixed point is in a constant ratio to which is distance from a fixed line. So that means the distance of the ellipse from a fixed point is in a constant ratio. So that means they did not say it is equal. Now it says it's in a constant ratio to its distance from a fixed straight line. So imagine we have the axis here again. Then we have the ellipse. So the distance of a fixed point, the distance of is the locus of a point moving in a plane. So the distance of a point from a fixed point is equal to the distance from a fixed straight line. So the distance of this point, let's say x, point P, from a fixed point. So an ellipse has two foci. So the distance from a fixed point is in a constant ratio to its distance from a fixed straight line. Now that straight line is called that straight line is also known as the directrix of the ellipse. So it is on either side of the ellipse. So we have one here, we have one here. So distance from here to here is in a particular ratio from distance from here to here. So we can say that PF, or we can say that ratio, the distance from fixed points to distance from a straight line, that is, let's say PF over PD equals to E. That ratio is called the eccentricity of the ellipse, and that ratio is determines how curved the ellipse looks, and it also determines the focal length of the ellipse, or the distance between the focus. So basically, that being said, we have That's with this the equation of an ellipse is gotten by manipulating some of these geometric properties of an ellipse, but I will not be concerning myself with that in this video. Now let's move on to the hyperbola. Now the hyperbola is kind of like when you split an ellipse and invert its two halves. So but the hyperbola is less known. When I was studying it, I did not even put too much effort into it because it's kind of a mirror image of the ellipse. Now you can check out the equations of all these shapes I'm talking about, but what I'm focusing here now is on the basic principle of how they look. So we have the hyperbola. Now the hyperbola is it looks like this. So if we have on the axis here, we have the hyperbola here. So and then we have the directrix of the hyperbola. Then we also have another half here and here. So basically, this hyperbola, it is basically the locus of a point in a plane which moves in such a way that its distance from a fixed point is in a common ratio, using a constant ratio e, which is greater than 1, to its distance from a fixed line. That means, and that fixed line, that line does not touch the point. That means this point, distance of this point, is in a constant ratio from a fixed point to a given straight line. So most likely we are dealing with on a fixed side of the ellipse. So from here to here of the hyperbola. Then if we have a point here, it will be from here, distance from this focus to the directrix, it must be in a constant ratio. So it doesn't matter whether you pick this point. If I pick another point here, the ratio of its distance from to this fixed point to the straight directrix will still be equal. So these are the rules. That is what is known as locus. Now these rules guide the shape of these figures. I'm very sure that mechanical engineers, they would have come up with different rules, and these rules they can invent different shapes which you've never seen before. So these rules, they are just rules that govern particular shape. You can come up with rules, you can just think of rules and like set up a locus, and then you can form a shape as a result. So you can, I don't know, but hopefully I might be doing a course on AutoCAD and drawing in subsequent videos. So hopefully let's see how creative we can go with locus. So that being said, I hope you've enjoyed this episode, even though it's quite scanty and no formulas involved, but I just made sure that I wanted you to understand the fundamental background of conic sections. Thanks for watching.